Last summer, I had the idea to make some roller skates out of Knex, but before I started building them, I wanted to know, will Knex axles support my weight? Having studied math in college, I approached answering this question by trying to prove the following proposition. Proposition 1. A skate with 4 wheels will support at least 160 pounds without the axles breaking. Okay, so let's see how we can prove this. First, we will need to make a drawing showing the forces acting on the axle at any one wheel. We will need to make the following simplifying assumption. Assumption 1. We can act as if the forces on the rods are acting at the edges of the sockets only. Alright, so now we can draw our little diagram here. First, let's just see what it's really going to look like. We will have an axle, we'll have a wheel, we'll have a spacer on either side because we don't want our wheel to rub up too much against the body of the skate. Whoops. So we got 2 spacers, and then we've got these 2 green pieces, which represent the sockets. That's the body of the skate. Let's make a little diagram showing this setup. This is one of 4 wheels on one of my skates. So just to be really clear about that, we've got our spacer here, we got our wheel in the middle, we got another spacer on this side, and then it connects to the skate here and here. Since there are 4 wheels, each wheel carries 1/4 of the weight, or 40 pounds. And I'm going to label these points A, B, C, and D. The skate exerts pressure down, force down on the axle. 20 pounds here, 20 pounds here for a total of 40 pounds down. And the wheel exerts force up on the axle. 20 pounds here, and 20 pounds here. So, what makes rods break anyway? I figure it is something like this. Assumption 2. If a Knex rod experiences a certain amount of torque in one direction, it will break. Recall that torque is force times the distance from a pivot point. And we usually write it as tau. So tau is equal to force times distance. Okay, so let us consider the torques when we look at A as the pivot point. Torque A is equal to 0 because the distance D is 0. Torque B is 1 spacer unit away. We're going to introduce a new unit here. Torque equals force times distance measured in pound Knex units, which I'm going to abbreviate KU. 1 KU equals width of one of these guys. Okay, so torque B is 20 pounds times 1 Knex unit, or 20 pound Knex units. Torque C is 20 pounds times 1, 2, 3 Knex units, or 60 pound Knex units. And then torque D is once again 20 pounds, so it's in the other direction, so we're going to have a minus here. So this force is down rather than up. It's a different direction relative to the pivot point, times 4 Knex units, or 80 pound Knex units, but since this is in the other direction, we don't care about it. We're not going to worry about that one. So the torques at B and C threaten to break our rod. If we assume that the torques at B and C do break the rod, then we might be able to find some sort of false conclusion, and we'll know that that original assumption that these two would break our rod is incorrect because we followed it to its conclusion and we got something that was not true. For the contradiction, assume the axle breaks under 80 pound Knex units of torque. Consider the following system. Okay, we've got a much longer Knex rod from A prime to C prime. That's a gray rod, not drawn to scale. It is 56 Knex units. And we've got a much smaller force here, a 3 pound force going down here in the middle. Treating A prime as the pivot point, the torque exerted at B prime is 84 pound Knex units because 3 times 56 over 2, that's halfway across our rod, is 28 times 3 is 84 pound Knex units. So, by our assumption, our rod should break because it is experiencing more torque than we have here. But this is a contradiction. This setup does not break the rod. So our assumption is wrong, and our axle would not break in our original setup, which is what we were trying to show. So in the setup detailed here, we just assumed that the axle would break, then we found a contradiction, so we can conclude that the axle would in fact not break. And we're done. Okay, so that is how I went about proving my statement originally, and I do think looking for these sorts of contradictions is a good way to come up with the idea for a proof. But arguments by contradiction like this one can often be written in a more elegant way. So let's give that a try. Proof 2. This time we begin with 2 assumptions and 1 observation. Assumption 1. We can act as if the forces acting on the rods are acting on the edges of the sockets only. And assumption 2. If a Knex rod experiences a certain amount of torque in one direction, it will break. Observation 1. A 56 Knex unit long Knex rod can support 3 pounds of weight at its midpoint. By assumption 2, rods do not break, therefore, under 84 pound Knex units of torque. This is what we just showed with our scale. We will now consider our same wheel axle system as before. We had our skates here, we have our spacers here, and we have our wheel in the middle. And then we will label our points A, B, C, and D, and we will draw our force lines. Each is 20 pounds here. By assumption 1, we can consider only these forces that are at the edges of the sockets. We take point A as the pivot point. We can calculate the torques. So torque at A is equal to 0 because the distance from A is 0. Torque at B is 20 pound Knex units. Torque at C is 20 pounds times 3 Knex units, or 60 pound Knex units. Torque at D is in the wrong direction, so we won't worry about that one. Since torque B plus torque C equals 80 pound Knex units, which is less than or equal to 84 pound Knex units, the axle will not break. We can conclude this by observation 1, and that's what we were trying to show. Ultimately, there was a third proof of sorts for my proposition, a pragmatic one. I actually built the skates and successfully stood on one foot in them. That's not to say they really ended up working, but you'll have to watch my previous video about the skates to see that. Anyway, I hope you enjoyed this video and saw how this kind of mathematical thinking can help you solve problems. Thanks for watching.